Whether your game is set in an urban environment, a medieval one, something dystopian, or something more optimistically futuristic, the majority of these settings have one pretty unavoidable thing in common: buildings. Buildings are everywhere in games, but from a development perspective, they're also kind of a pain. There are about 1,000 different ways to make buildings. You can hand place modular pieces one at a time, like you're playing with Lego. You can go full procedural and let an algorithm generate your city, which sounds cool until you realize it's an entire person's job to do just that one thing professionally. Or why bother? Maybe you just toss a couple of low poly cubes in the background and call it urban minimalist. The point is, there's no one right way to do it. Each game and each project has its own set of demands, and each team will have different ways they prefer to build out their levels or environments. But the main thing that it's safe to assume is that these teams have tools to help them make this potentially incredibly painful and time-consuming process a lot less, well, time-consuming and painful. So in this video, I'm going to walk you through the tool I built to generate buildings for my game using splines and modular mesh pieces, something that gave me the flexibility that I needed without the pain of micromanaging every single brick. Hi there, I'm Matt, and welcome to Game Dev Guide. In this episode, we're going to look at how we can use Unity's spline tools to help us lay out wall and window meshes and procedurally generate the shell of a building for us to use in our games. We're going to look at how to place points along a spline and procedurally align mesh pieces around it, as well as how to select different reference pieces, such as windows and doors, and merge those into our mesh too. Once we've done that, we're also going to look at how we can build tools for customizing the shape and size of our building, allowing us to simply drag a tool in the scene view to change our height and more naturally integrate with our spline editing workflow. We'll then finish off our building mesh by procedurally generating a roof that we can also customize and adjust. And finally, we'll look at how we can bake out our final mesh into the project so we can make instances of it elsewhere in our project or in other projects entirely. Before we dive into it though, I'd like to take a moment to thank the sponsor of this video, Xsolla. If you're a developer currently watching this and working on a mobile game, then Xsolla's web shop might interest you. Historically, mobile devs didn't have much of a choice if you wanted to sell in-game currency or items. You had to go through the platform's storefronts and lose about 30% to platform fees. We all know how painful that can be, especially when it feels like you're fighting amongst everyone else to get your game in front of people. That 30% adds up when you're not getting much in return. But the good news is that thanks to some rather infamous legal battles, times are changing and developers in the US can now link players directly from their iOS apps to a browser-based checkout without breaking any rules. Xsolla Web Shop gives you a custom branded storefront that you can build without needing to code anything, where players can buy directly from you. Xsolla Web Shop handles in-game currency, bundles, passes, or whatever else you might be selling, and their payment system supports over 1,000 different payment methods. Instead of the 30% cut platform holders take, the transaction fee is around 5%, so you keep a lot more of what your game earns. There are also built-in tools for running promotions, offering special bundles, and managing live ops without writing extra systems yourself. So not only are you saving on the upfront fees, but you're also getting better control of how you monetize and engage your players. Xsolla's been doing this a long time. They're one of the few companies in this space that understands how to scale with your game. It's already being used by some of the biggest names in mobile, but you don't need to be a big studio to take advantage of it. Setup is quick, integration is lightweight, and it just works. So if Xsolla Web Shop sounds helpful, you can follow the link in the description or scan the QR code on screen now to check it out. Thanks again to Xsolla for sponsoring this portion of the video. Now let's design our procedural building generation tool. As I'm sure you're already aware, there are a lot of different ways developers can generate buildings for their levels. Some go all in on procedural systems that simulate complex architectural logic to produce detailed, varied structures. Others go fully manual, hand-placing modular meshes and snapping them together like Lego. And then there are options somewhere in between. Ultimately, the best approach is the one that's easiest and makes the most sense for your game. For me, that's this spline-based approach that I'm sharing with you today. I find that it strikes a really nice balance between flexibility and control. My game is all about racing around a city and picking up passengers. The city is definitely part of the experience, but I don't need to spend an absurd amount of time crafting intricate details that most players will just speed past. I just need the environment to feel like a city with enough variation to avoid repetition, and not look obviously wrong or out of place. I'd rather spend my time refining the gameplay. So, I built a tool that lets me lay out buildings by drawing splines. It places pre-made mesh pieces of my choosing along the curve, so I can quickly block out shapes, make changes by moving points or swapping meshes, and maintain consistency across the map. Hand placing every piece works fine for small scenes, but for a whole city it would have become tedious fast. Full procedural generation could offer more variety, sure, but it's harder to steer towards a specific result or refine something once you have it. The main trade-off is that this system relies on meshes that work well along a spline, so it's not great for intricate designs or complex roof shapes, but for the scale and purpose of my project, it gives me what I need without slowing me down. And if I do want to get more detailed later, I can always add extra touches by hand on top of the spline generated meshes. So with all that in mind, let's take a look at how we can start putting a tool like this together. I have a mostly empty environment scene here, and so I'd like to fill it with buildings that we procedurally generate. As you can see, I've got 3 meshes here: a wall mesh, a window mesh, and a door mesh. What we're going to do is write a tool that will generate points around our spline based on the width of our mesh pieces, and then randomly place each mesh piece according to our parameters. To get started then, let's make sure we have the spline tools downloaded by going to Package Manager, Splines. Then let's just quickly draw out a spline here. And then let's create a new script which we'll call Building Maker. This will be one mega script that's eventually going to generate each building for us. For now though, let's just get it to generate our points for us. In here, we'll add the require component attribute and make sure the object has a spline container. We'll also add the execute in edit mode attribute so that our script can run while we're editing. In our awake method, let's assign our spline container to a local reference. We're going to dynamically calculate our distance based on the mesh we supply, so let's add a reference to all 3 of our meshes and then let's add a variable for distance. As we're working on this in the editor, let's use onValidate to update some of our stats whenever we change things in the inspector. So let's use the bounds of our wall mesh to set the distance property. My meshes are oriented along the x-axis, so we'll use this to calculate its width. Next then, we should calculate the length of our spline and designate points along it to instance our mesh pieces onto. Let's make a new method called calculatePoints and call it in our onValidate method. In here, we'll create a new list of point vectors and a new list of tangent vectors. We'll then get a reference to our main spline on our container and evaluate the position and tangent at the 0 point on the spline. Then we'll use the handy getPointAtLinearDistance function on the spline to calculate the t-value after moving along the spline by our wall's size. We'll then use this in a while loop to iterate over our spline and assign each point and tangent until we've moved all the way along. If we check in the inspector, we should now have a list of points along the spline. When I'm doing things like this and building more complex scripts piece by piece, I always like to visualize what I'm doing a little more easily, as it's sometimes difficult to spot mistakes when we're just looking at a list of vectors in the inspector. So I like to take advantage of scene gizmos. Placing this loop in the onDrawGizmoSelected method will allow us to visualize all of our points while we're working on our script. As you can see, we now have evenly placed points along our spline. If we make any changes though, notice that our visualization doesn't update. Let's add a way to listen to changes on the spline and trigger an update. We can do this by using the static spline.change callback. So let's add a listener into our onEnable method, and let's also make sure we unsubscribe onDisable. Then when a point is now moved on our spline, we recalculate the points and update our generation. Now, as we move one of our spline points around, you can see that our points update and our visualization changes accordingly. At this point, we're now ready to start instancing our mesh pieces along the spline. Basically, what we can do is go from point to point instancing our mesh piece and then merge it with the previous one, so we end up with one single mesh piece. Let's start then by setting up our tool to generate a mesh. We'll begin by adding a child object that holds all of the things we'll need to generate a mesh. Then we'll set up a list of combined instances. This is just a helper struct in Unity that is used for metadata about how 2 meshes should be combined together. We'll make use of this in a bit. We'll then make some variables for our position, as well as an offset matrix that will help us point our mesh in the right direction along the spline. And we'll make an instance of a combined instance and an instance of our wall mesh. We're now ready to iterate over our points and assign our mesh pieces. In our for loop then, let's get the direction of our current point relative to the next one and assign our current point position. We'll then calculate the look direction for our mesh. We want to make sure that our mesh is aligned with the spline correctly, so we'll swap the Z and X values over in our vector here, otherwise our wall front would end up facing the direction of the spline instead of our wall edge. Next, we'll assign the offset matrix. This is essentially just a position, rotation, and scale command all in one. Finally then, we'll iterate over the submeshes in our wall mesh and provide a combined instance for each one. This allows us to make sure that when our mesh is combined, all of its material data remains intact. Right now, this wall is just using a single material, but we're going to be using meshes with multiple materials eventually, so this will save us some headaches in the future. So our loop is now iterating over our points and generating mesh data for us to use inside our instances list. But we're not quite done yet. If you look here and we take this list and combine them all together using the combine meshes method, each mesh renders as its own submesh. As we add materials to the stack here, we're revealing the next mesh piece. And this is basically just due to how the combine instance struct and combine meshes method work. The combine meshes method ultimately just makes a new submesh for every instance of combine instance supplied, so it's making a new submesh for every point along our spline. If we switch to using a mesh with multiple materials, you can see that we're actually making a new submesh for every material in every mesh for every point. This is obviously not what we want. Instead, our desired result is just to make sure that meshes with multiple materials are maintained and that our final merged mesh keeps the material data from the base pieces that we supply. So what we should be supplying into our final mesh is a list of combined instances that represent the mesh data for each material instead. Exiting our loop then, we'll create this combine by submesh index method and pass in our instances list. In this method, we'll go over all of the supplied instances and sort them by their submesh index. Then we'll merge each group that share the same index into their own single instance, representing that submesh as a whole. Notice that when calling combine meshes here, we're setting the parameter to true, which builds a single merged mesh for the supplied data. We'll then use this mesh data to return a new combine instance struct that represents the piece of the mesh for any given material. We'll also need to provide the mesh with data about its submeshes, so let's create a method called instances_to_submesh_data and pass in our instances. In this method, we'll iterate over our instances, and for every entry, we'll get the triangle counts and build a submesh descriptor and add it to our list. Then, after combining our meshes, we just set the submesh info using our list. And now, back in our scene, we have a series of joining pieces together to form our wall shape, and the mesh is correctly split up based on the materials on our object. This is excellent. As we move the spline points around, our tool responds and generates a new mesh to match. As I'm sure you've noticed, we have one little gap in our mesh here, and it's not always the same size. This is just the remainder piece that's left after moving around the spline at a fixed distance. So, what we can do is use our base wall mesh to fill in this remaining distance and complete our shape. In our for loop, let's now count all of our points, and at the top here, we'll check to see if we're evaluating the last point, and if we are, we'll calculate the remaining distance. We'll then set our direction based on the first point in our array, and we'll simply set the scale along the x-axis as our distance divided by our width. Now we have a final section of wall that scales to fill the remaining space. Pretty neat. One of my favorite things about this tool is how it adapts to the shape of our spline. As you can see, if we set our spline to auto, our wall pieces rotate and position themselves along the curve of the spine. It affords us the ability to create really interesting building footprints. Speaking of which, we have our wall, but we'll need doors and windows in order for this to start resembling a proper building, so let's add support to our tool for choosing additional mesh shapes here. Thankfully, it's now a pretty simple process to do this. In our maker script, let's add a new property for the window distribution. Then in our generate mesh method, let's break up our instances. We'll make a wall instance and a window instance, and then designate a selected mesh property. In our loop, we'll check the window distribution, and if it's set to 0, default to choosing our wall. If it's set to 1, we'll do a dice roll, or if it's above 1, we'll use a modulo operator to place the wall evenly based on our current point index. Then we just change the mesh we're assigning in our combined instance to our new mesh variable, and in our scene, our wall now has windows. Let's do the same thing for selecting a door. We'll make an additional property for door distribution and also set a property for max doors. In our method, we'll reference our door mesh and also start a count for the current doors we've selected. In our loop, we'll add another section for our door using the same logic as before. Now our wall has both doors and windows, and our shape is starting to look more like a building. So this is looking pretty good, but our building is a little short. We should probably add support for more floors and build additional layers on top of our existing mesh. Let's add a variable for the number of floors, making sure that we at least generate one floor. And in our mesh loop, let's wrap this around another for loop based on the number of floors we want. Then all we need to do is make sure that we only place the door if we're in our first floor loop, and we offset the position by the floor index and the height of our base wall mesh. And just like that, we've turned our single-story complex into a monolithic mega tower. It's kind of annoying having to fiddle with this every time we want to increase the height of our building though. especially when it's already so responsive to our spline shape. So let's quickly add a scene gizmo that will let me adjust the height of our building more intuitively. In our project, let's make a new script called Building Maker Editor. We'll set this as an editor for the Building Maker script, and we'll make sure to create an instance to it. In our Building Maker, we'll update a few of our properties here so we can get references to them. And then in the onScene GUI method of our editor script, we'll calculate the center position of our building by adding all the points together and averaging them out. We'll then get a reference to the height of a single floor by fetching the data from the wall mesh assigned to the tool, and then we'll figure out where the floor is, as well as the current top of the building. Then all we have to do is draw a few gizmos and add a free move handle. When the free move handle has been touched, we'll calculate the new position by removing the initial position of our building and dividing the Y position by our height value. This gives us the number of floors to set. Finally, we'll call onValidate on the building script so that it updates. We now have a handy tool in the scene view that we can drag up and down to change the building height, and we can now, quite swiftly, make edits to both the building shape and building size with ease. The only major issue now is that our buildings are obviously hollow. There's a big gaping hole in the middle here, so let's just take care of that and put a hat on our building in the form of a roof. Roofs come in all shapes and sizes, so there are probably a million different ways we could do this, and I've explored a few of them in the past while developing this tool, but ultimately I ended up settling on the simplest solution of just filling in the shape and extruding a procedural roof from there. The player isn't really going to be spending a lot of time observing the rooftops, and I didn't want to spend a ton of time on it honestly, so I'll show you the way that I achieved this, but it's by far the least elegant and results in a pretty simple roof shape. In our building script, let's add a final method for generating a roof. We want the roof to be our final submesh material, so let's start by adding a method after we combine our submeshes by index. We'll call this method buildRoofMeshData and pass it to our instances list. We're also going to build a couple of helper structs that will make procedural mesh generation a bit easier. Let's make a new struct called vertexInfo. This one is pretty simple. It essentially holds key metadata for each vertex, and when we're working on our mesh procedurally, allows us to swap data in and out, making the final generation process a lot easier. Then let's also add a new struct called quad. This struct will help make sure that we're making enough verts to properly texture and UV map our mesh, as well as making it a lot easier to process triangle indices when building the mesh. In here, we'll take an offset parameter and a list of vertex positions for our quad. In the calculate UVs method, we'll just procedurally generate some UV data based on the distance between each vertex. And a set triangles method simply grabs the index from each vertex info struct. Then we also provide 3 methods for grabbing each list of data, which we'll need when building our mesh. Now then, let's start generating the info for our roof. We'll start by grabbing the center point and we'll add a potential offset to it too. Then we'll calculate the verts by iterating over our points. For the mansard roof approach, we want to make sure that our 3rd and 4th points can move between the base point or the full center point. So we'll lerp between the two based on the edge point value. Then we'll offset our points by the total height of our base mesh, and we'll create new quad data and add this to our list of faces. Then we'll create a new method called getMeshFromQuads and pass in our faces. This method will simply iterate over each quad and collate all the data we need into lists for the mesh. Back in our roof method, we'll build a new combine instance and return it. Now, back in Unity, if we add an additional material to our renderer here, we can see our roof. If we adjust the height value, we can determine the slope of the roof. If we adjust just the edge point though, we can create our hipped roof edge. All we need to do now then is fill in this hole and get our mansard roof shape. Underneath our first set of quads, let's add a check to see if our roof edge point is less than 1. If it is, we'll total the current number of faces. And we'll also calculate our new roof flat point by copying the center point and subtracting the additional offset, lerping between the value based on our edge point. Then we'll loop over our quads and make some new quads by grabbing the top edge of our previous quad and adding our 2 new points in the center of the roof. Then we'll add this to our faces list. Now we have a roof edge with a flat top. Like I said, it's pretty simplistic, but it offers enough variety of roof shapes for me. And that's pretty much all there is to it. We now have the ingredients we need to generate believable city buildings quickly and easily. You can see here just how in a few clicks I can make different shapes, colors, and styles of buildings. I can merge 2 building shapes into each other to make more interesting footprints, And by swapping out the mesh variations, I can also change how each building looks. The coolest thing about this method for me is that as I'm laying out my levels, if I want to make changes to existing buildings, I can do it in just a few seconds. Minor adjustments are super easy and relatively non-destructive, giving me so much more flexibility when I'm laying out my levels. I can work on an area and come back to it later without any huge knock-on effects. One thing we ought to do though is make sure that if we're happy with how a building currently looks, that we don't lose that data. As you can see here, if we're set to a more random distribution of assets, every time we reset our script, our building re-rolls. There are a few things we could do to fix this, such as storing a specific distribution seed, but the simplest for now is to simply add a lock toggle. In our building maker script, let's add a lock boolean, and when set to true, the building won't regenerate automatically until it's unlocked. Now our building mesh will remain static until we unlock the script, no matter what. As a final measure then, if we're happy with our building and would like to use it elsewhere in our project or export it out, we can actually bake our mesh data into our project. This is especially useful if we're on the final pass of our scene and we're optimizing assets. We can simply write a mesh baking script like this one that will save the asset into our project directly. We can then drag it from our project window into the scene for use at a later date. And that's about it for today's video. We now have a pretty flexible tool that makes it easy to procedurally generate a variety of buildings throughout the level. By using different source meshes, I can quickly create interesting, varied structures that give the city some personality without a ton of manual work. If you've caught any of the streams on the channel, you've probably already seen how much I enjoy using this tool. It's been a core part of how I'm building the map for Cabs of Chaos. It's fast, easy to use, and solves a real problem I was facing when trying to design a city scale level. As I'm sure you can tell, this is very much a starting point, so I'm very interested in hearing about what you'd be likely to do with this tool and whether or not this video has helped you. If you've enjoyed the video, don't forget to hit that like button and be sure to leave a comment down below and let me know your thoughts. If you're new to the channel, then please do consider hitting that subscribe button as you'll be notified when new videos go live. Or if you'd like to see more from me first, then consider checking out one of the videos on screen now. As always, thank you very much for watching, and I'll see you again next time.